Okay, that's our course is physical basics of multimedia systems. Physical basics of multimedia systems, and physics. Physics consists of some different topics. For example, kinematics, kinematics, electricity and magnetism, atom physics. We will start with kinematics. Kinematics because this is a base. This is a base for whole our course. So let's begin with this. Let's begin with this. Kinematics is a part of physics that devoted to motion. It considers motion without considering different factors that can affect motion. I mean these factors like forces. Forces we will study later when we study dynamics. So kinematics we consider motion without factors that can make effect on motion. And we have to say something about different objects. Different objects are considered in kinematics. The main object of kinematics is material point. Material point. What is material point? How to understand what is this? First of all, material point is a point that has it can be considered like a geometric point that has mass. And has no size. Sometimes it is possible. Sometimes it is possible to study and consider real object from real world, like material point. For example, if we consider motion of Earth satellite, without studying its rotation, it can be considered like material point. The next object, other objects are perfectly rigid body, perfect liquid, for example, elastic media, but all these objects can be considered like material systems. Material systems are systems of material points. So if we understand some properties of material point, we will be able to understand properties of any material systems. So let's study properties of material point. To study properties of material point, to study its motion, we have to set a reference point and connect reference system to this. I think you know what reference system is. There are different types of reference system, and the most common is Cartesian rectangular coordinates. I mean something like this. Three axes x, x, y, and z. Three axes, because we have three-dimensional space, So to set point, we have to set three values. When we set this, we can find our material point. It can be written like this. M in brackets x, y, z. I think you understand what does it mean. And I have to say something about coordinates of pixel on the screen. How to set pixel on the screen. It is obviously that we need two values to set where the pixel is, but reference point in this case is in left upper corner of the screen. So reference system looks like this. If we are talking about pixel on the screen, x, y. Reference point in the top left corner. Do you have any question? No. Okay. Let's continue. Another way to set point in the space is to set this by radius vector. What is this? Radius vector, it can be described like this. It is a vector that begins in reference point, and it has end in material point. And if we set some unit vectors like this, E, J, K, if we set these orts, we can connect our radius vectors and Cartesian coordinates E, J, and K. I hope that you have already studied geometry, vector algebra, and you will be able to understand what I am talking about. So radius vector is x, e plus y, j, and plus z, k, a. And it is obvious that coordinates x, y, z can be changed in time. So they are functions of time. It can be written like this. X is a function of time. Y is a function of time, and z is also a function of time. Oh, sorry. Z is a function of time, like this. And of course, radius vector is also be a function of time. This equation, these equations are also called kinematical equations of motion. Kinematical equations of motion. If we get a time t from this, if we exclude t from this equation, we will get equations that is known as trajectory equation. Okay, maybe for example, if we have x is equal a t, y is equal b t in second exponent, we can exclude t from first equation and make substitution like this, and we will obtain y or y is equal to b in denominator we have a in second exponent, and here we have x in second exponent. So this is trajectory equation. This trajectory equation. Trajectory is a curve, and material point moves along this curve. Material point moves along a curve that is called trajectory. Do you have any questions? No. Okay. Okay, that's great. Let's go. Let's go to next step. Okay, let's imagine this. Let's imagine this. Consider that material point is here, and it has radius vector r1. In moment of time t. In moment of time t, it has radius vector r1. Okay, next time it can be in another place that can be described with radius vector r2 like this, r2, and the way is a part of trajectory ds, and how to describe the movement of material point in this case. We can describe this with so-called displacement vector. What is displacement vector? Displacement vector begins in initial point and ends in end point. final point. It can be signed as delta r. Delta r. According to this picture, we can say that delta r is equal to r2 minus r1 and it also can be written like this: r in moment t plus delta t plus delta t minus r in moment t. Do you have any questions about this? Is everything clear?
Yes.
Okay, that's great. And if this motion were during time delta t, we can say we can set average displacement velocity like this. Average displacement velocity. It is
Teacher, could you please repeat the name of this part?
I'll write this. Just a moment. I'll write this. Average displacement velocity. Yeah, this average displacement velocity t plus delta t r from t and divide by delta t. So we can draw this red frame because it is important formula that we will use it in future, and we can use such frame here too. Yes, okay. What about this velocity? Is it useful? Sometimes yes, but sometimes no. What problem with average velocity? The problem is that this velocity can change during the motion. And these problems with change in velocity will be more for long time. So if we have long time, average velocity is not useful because velocity of motion is different during in different time moments. So what to do in this case? We can remember something from mathematical analysis. And remember, for example, this. Let's have a look at this question. At this, have a look at this picture, and maybe you can remember from mathematical analysis that we can write something like this. dr is equal to absolute value of dr, and this is equal to limit delta t to 0, displacement vector delta r, and it is equal to limit delta t to 0, delta s d equal to ds. No, ds. So when we use very small delta t, limit delta t to 0, the length of way will be equal to absolute value of displacement vector. Is it clear, or you have some questions about this? No questions. Okay. And this is the key. This is the key to understand how to describe velocity. How to describe velocity in direct time moment. So we can do it like this. Velocity v is equal to limit delta t to 0, average velocity, and it is equal to limit delta t to 0, and let's make substitution like this. R in t plus delta t minus r in t, delta t. And can you remember from mathematical analysis what does this mean? Can you remember this? Okay, maybe you can remember this in this way. Limit delta x to 0, function f from x plus delta x minus f from x divided by delta x. Can you remember what is this from mathematical analysis? Do you hear me? Dear students, do you hear me now?
Yes, teacher.
teacher.
Yes, okay. So, could you please remember what does this mean from mathematical analysis? Okay, I'll remind. It is the definition of derivative. df by dx. Definition by derivative. Derivative is derivative can be understood as velocity of changing of function, velocity of function change, velocity of function change with changing of its argument. The bigger derivative, the faster function changes with changing its argument, and it can also be signed as like this. It is from mathematical analysis from your first year of education. First year of education, I just reminded this to you. Okay, and if you compare this and this, if you compare this and this, you can understand that it is almost the same, So it is the derivative of a radius vector r by time, dr by dt. Do you have any questions about this? Is it clear or not? Maybe something is difficult or unclear.
What does this formula to you?
Without oh, I don't hear you now.
What does this formula to you?
What
What does this formula use?
what is the use of this formula?
Yes.
Yeah, I will show you later.
Okay.
Because it is
And
a definition of velocity. It is a definition of velocity, and we have to know velocity. We have to know velocity. For example, we are riding by car from A to B. We are riding by car from A to B, and we want to know how much time it will take. How much time it will take to get from A to B, and to calculate this time. To calculate this time, we need to know velocity. For example, if the distance between A and B is 100 kilometers, for example, and velocity is 50 kilometers per hour. 50 kilometers per hour. We can calculate that 100 kilometers divided by 50 kilometers per hour, it results 2 hours. So velocity velocity is necessary to describe motion. To describe motion, this is the use of this physical value.
Okay, teacher, and one more question.
One more question,
This
okay.
this this formula is to use to calculate the to calculate the velocity of this wave, right? Or
This
with
formula,
one moment.
one moment.
One
This
moment with the velocity.
I have bad sound, and I cannot hear you well. So
This formula is used to the one moment the velocity. This formula is used to the velocity of one moment.
velocity at one direct moment of time.
Direct moment.
One direct moment. One moment t. Not time period. Not time period. Not time span. And concrete moment.
Okay.
I will clean some information from my screen because I need some place. I need some place to write some more information on this. And this is instantaneous speed. Instantaneous speed. Definition of instantaneous speed. Definition of instantaneous speed. And I will draw a red frame because it is important definition for our further education. Okay, I hope that it is clear. So delta t time span is to 0. It is very small, and it allows us to consider speed in time moment t. Okay, and in the same way we can define acceleration. Acceleration is a speed of speed changing. And it is first derivative from speed. Okay, let's get this first derivative, acceleration. Acceleration a is equal to first derivative from velocity by time. And maybe you can remember from mathematical analysis, first derivative from first derivative. what will we have in result? What is the first derivative from first derivative? I mean this. I mean this. D by dt from dr by dt. What will be in result? Can anybody remember this from mathematics? But it will be second derivative. D2r by dt2. Okay, so we can make substitution. D2r d by dt2. Okay, is it clear?
Yes, teacher.
Okay, that's great. That's great. So acceleration. Maybe it is necessary. Maybe it is necessary to do one more thing. Let's make
Teacher, could you
substitution.
come back from the previous step?
What
Sorry.
step?
The explanation of the acceleration.
Definition of acceleration.
The formula of the mathematical analysis.
Formula for mathematical analysis. You mean this?
Yes.
This?
Yes.
And what's wrong with this?
No. No.
Or something is unclear about this.
I understand. Thank you.
Sound is very bad. Sound is very bad.
I understand, teacher. Thank you.
Okay. That's great. That's great. Let's continue in this case. Okay, let's make substitution. Let's make substitution like this. So v velocity is equal this derivative. Is equal this derivative plus y dot and plus z k. Do you remember how to open such brackets? How to open such brackets? It is also from mathematical analysis. maybe you will remember this from mathematical analysis. How to open these brackets? It is necessary to remember how to get derivative from linear combination of functions.
You multiply the derivative of f(x) and plus derivative of g(x), right?
I don't hear. I have heard something about multiple. Yes, it is better if you. Oh, great. Yes, that's right. That's right. Okay. Okay. It is very well. It is very well. You understand. You understand. You remember. You remember mathematical analysis. So we can use this in physics. We can use this in physics. Words I, J, K are constant vectors. So we can write like this: dx by dt I plus dy by dt j plus d z by dt k. Something like this, and we can make signation. We can make signation. I mean, we can sign like this: v x v y v z v z. So we have v x I plus v and plus v z k. So we have written this vector of velocity with components of this vector. Components vx, vy, vz. Maybe if we want to know absolute value of velocity, if we don't want to know direction, we want to know absolute value. How will we find this? We can write something like this: v without vector, without arrow, on this. We can write like this: absolute value. And do you remember how to find absolute value of vector? Absolute value, it is the same as length of vector. Okay, I will remind. It is It is square root from sum of squares. It results from Pythagoras theorem. Can you remember this? From vector algebra. Do you hear me?
Yes, yes.
But cannot remember this formula. Okay, if you cannot remember, you should say this. I will remind you. I will remind you. This is no problem if you forgot something. It is common situation. It is common situation. So nothing bad in this. It is normal. I can remind this formula. How can we understand the length of vector? Let's draw this reference system or Cartesian system. I will consider two-dimensional system. In 3 dimensions, the situation is the same, but it is more difficult. It is more difficult to draw this. It is more difficult to draw. And how can we describe vector? Vector from, for example, vector A. It has components ax and ay. Let's find them. I'll draw such lines that are normal to coordinate axis. I'll draw such lines. I'll make them dash. I'll make them dash. I'll make them dash. I'll make them dash. And so we have vector components. Vector components are equal to these distances. This is a x component, and this is a y or y component. Ay, and the vector a can be written in these coordinates. Can be written like this: a x e plus a y j plus a y j. And how can we find the length of vector a? Length is the same as absolute value of the vector. Oh, yes, this is correct. And this is correct. And so we have the key to understand this. This is the same, because but here we have three-dimensional case, but our logic in three-dimensional case is the same as in case that was two-dimensional. Yes, thank you. I see you understand. I see you understand the material, and this is very good. Okay, I will clean my screen. I will clean my screen to free some space. On it. Okay, let's make substitution. If we do this, we can write something like this: dx by dt in second exponent plus dy by dt and plus dz by dt. By dt in second exponent. What we can see here? In every add we have dt in each denominator. In each denominator we have dt in second exponent. So dt can be get from the square root. Dt can be got from the square root. If we can do this like this: dx in second exponent, dy in second exponent, and plus dz in second exponent. And here in denominator we have dt. Okay, is it clear or not?
Yes, it's clear.
Okay, and this square root is equal to absolute value of dr. And because dt is non-negative, I can not to write absolute value. I can write is as dt simple, without brackets. And as we can remember, we have talked about this a few minutes ago, that absolute value of dr is equal to ds. So we can write this. We can write this like ds by dt. ds by dt. So absolute value of velocity is equal to derivative from way by time. Derivative from way by time. Okay, do you have any questions about this? No questions. Okay, let's talk. Then let's talk about acceleration, more particularly about acceleration, because it is necessary for us to understand all properties of acceleration, because without this understanding we will not be able to solve exercises. So let's talk more about acceleration. Now I need to free some space on my screen. I need to free some space, and okay, maybe okay, let's leave this. Sometimes if we have motion along some curve, motion along some curve, we need to consider, and sometimes it is useful to consider acceleration like a sum of tangential and normal of acceleration. I mean this. We can consider A like as sum of tangential acceleration plus normal acceleration. Normal acceleration is also called sometimes radial acceleration or centripetal acceleration. So normal, radial, and centripetal acceleration is the same. What do I mean? I mean, I'll try to draw some pictures. This is trajectory. Velocity of material point is always tangential to trajectory. Velocity is always tangential to trajectory. But what about velocity? Velocity can be considered like sum of tangential and normal vectors. Now I'll try to draw this. Okay. Try to draw is tangential velocity and normal. The sum of them is, I said velocity. A is acceleration, tangential acceleration and normal acceleration. Sum of this acceleration, normal and tangential, is full acceleration or simple acceleration. So this is formula, and this is picture that shows this formula. Okay, how can we calculate tangential and normal acceleration, and what do they mean? Tangential acceleration describes changing of velocity, changing of absolute value of velocity And the normal acceleration shows changing in direction of velocity. Is it clear or something that you cannot understand in this? Okay, and let's draw some words here. Unit vectors tau, r, o, and n. Tangential and normal vectors. As you can remember, absolute value of tangential unit vector is unit. It is obvious, and absolute value of normal vector is also unit. And we can write this like this, in this way. The derivative from absolute value of velocity by time multiple to tau plus v in second exponent divided by r I have written this formula without proving it, but this is because I have no time. We have no time to prove everything, because this course of physics, it needs 1.5 years. 1.5 years to study this, but we have only one semester, only half a year, so we have no time to prove any formulas, and because of this I have to write some of them without proving. But if you have some questions, you may ask them.
Teacher, what is it at the definition of the acceleration, the right side?
This
No, yes, but right side.
right side, this
No, from acceleration.
from acceleration, where do you mean this?
Definition of the acceleration, but the right side.
This
Left.
this is definition of absolute value of velocity.
Yeah, I understand that. The left of that. D2, yes, right there.
Right, that. And what is unclear about this?
I don't understand which what how to say D2 and what is that?
What is this?
No. Yeah, D2. Yeah, right there.
Here, this.
Yes.
It means second derivative. Second derivative, let me explain. For example, df, it's from mathematics. Df by dt can be signed like f from x, first derivative. But second derivative d2f dx2 can be signed like this. And it is the same as f in this way. Or it can also be written like this. How to say this? D in brackets d f by d x d x. Or this is the same as d by d x df by dx. Okay, is it clear now?
Yes, teacher, it's already clear. I just didn't understand what that letter is.
It is number 2. It is number 2.
Okay.
Yes, I have some problems in writing. It is from school, and I couldn't manage. I couldn't manage to study how to write in proper way. This is a problem, and I don't know what to do with this. And, but I'm happy that computers sometimes helps me to do something, because I can just print something, not to write by hand. Okay, second derivative. It is number 2. It is number 2. Maybe it is necessary to write this in this way. Okay. Okay, so this is a formula. It is necessary to write a tau is tangential acceleration. Так, acceleration. Так, tangential acceleration, and an normal. Normal acceleration. Normal acceleration. Normal. What I can write, print like this. Normal or radial, comma, or how to print this in centripetal acceleration, or centripetal acceleration. So we can draw red frame, because it is also important formula. And when we if we have got tangential acceleration and normal acceleration, we can calculate full acceleration. In vector form, it can be written like this. In vector form, in scalar form, we have this formula. Tangential acceleration in second exponent and normal acceleration in also in second exponent. Also in second exponent. Also in second exponent. Okay, do you have any questions about this? And I can print more. I can print more changing of absolute value of velocity absolute value of velocity and here we have here we have changing of direction of velocity. Yes, is it clear? Because we have to consider two types of acceleration, tangential and normal, to understand how velocity change by its absolute value and how it changes by its direction. Because velocity is a vector value, it means that it has absolute value, it has length, and it has also direction. It is one of properties of vector values. Okay, maybe let's consider. Let's have a look at the rotation of perfectly rigid body. Perfectly rigid body. What does it mean? It means perfectly rigid body is a material system. So material system is a set of material points. So a perfectly rigid body is a set of material points that cannot move. That cannot move in relation to each other. It cannot move in relation to each other. For example, perfectly rigid body can be considered like two points. In the simplest case, 2 points. For example, A and B, and the distance between them cannot be changed. If the distance between A and B cannot be changed, these two material points are perfectly rigid body. It is the simplest case. Of course, perfectly rigid body is abstraction. It doesn't exist in real world. But it is useful. It is useful because there are many objects. There are many objects in real world that can be described like perfectly rigid bodies. So we need to understand them. We need to understand them, and let's do this. Let's do this. I'll try to draw some picture. I'll try to draw picture. Let's have a look at a perfectly rigid body that rotates around a fixed axis. Around fixed axis. It is usually this axis usually called as axis of rotation. And let's set a reference system. And axis z of this system we will direct in the same way as the axis of rotation. So v is axis of rotation of rigid body. Axis of rotation is fixed now. It cannot be changed. X, y, z, x, y, z. And if z is the axis of rotation, different points of rigid body, moves around circles. They make circles with centers are lying on the axis of rotation. And this is the key to understand how to describe rotational motion. Let's see. Let's consider that in first time moment we have radius vector r1, and in the second moment we have r2. R2, R1. Oh, that's bad. We have not enough space here. R1. And after time period delta t, we have some rotation by angle d phi. If we have turn by angle d phi, we can define angular velocity. Angular velocity is the first derivative from angle by time. So we can write angular velocity. Angular velocity. And this is a question. How to connect linear velocity and linear acceleration with angular values. With angular values. In the similar way, we can define angular acceleration. Angular acceleration. Angular acceleration. Angular acceleration. It can be signed like beta. Sometimes it's signed like epsilon, but it is not significant difference. D omega by dt. First derivative from angular velocity by time. And it is equal d 2 from phi by d t in dt 2. Angular acceleration and angular velocity. Do you have any question about this? No, okay. So we have the end, or almost the end of our lesson. Maybe if you have some questions, you can ask them. Or if you don't have questions, we can end our lesson. We can finish for today.
Okay, teacher.
Okay, don't have questions. Okay, so if you don't have questions, I have to thank you for your attention, and I will wait for you for the next lesson.
Okay, teacher. See you next semester. Goodbye.
Have a good day, teacher.
I don't hear.
Thank you, teacher. Have a
Goodbye,
nice day.
teacher. Thank you.
Thank you, sir.
Okay. Thank you, students. Thank you, students. I will wait you for next lesson. Okay, bye.
Bye-bye. Bye.
Bye, teacher.